I want to write down a proposition and end this lecture with that, to give you an idea of how better upper gradients do give us a lot of information. And later we will, of course, continue the study of upper gradients and later weak upper gradients and get into much deeper stuff. So the proposition is that if rho, remember again, so before we get used to these notions, I want to repeat. If this function, which is Borel, is an upper gradient of u along gamma and integral of rho along gamma is finite, then u is absolutely continuous on gamma, which in particular, remember, we allow u to also take positive and negative infinity values, but this shows that in particular u is never plus or minus infinity. Okay, so this is saying that if you have an upper gradient, which is small in the sense that its integral over the whole curve is finite, then you do get absolute continuity of the function along a curve, which is quite strong. Well, how do we prove? So we need to show that u composed with gamma, which is from AB into R, but initially we also know that maybe plus minus infinity, is absolutely continuous. That's because that's definition of u being absolutely continuous on gamma. Remember, gamma is non-constant, and we've assumed that its arc length parameterized. Okay, so take pairwise disjoint collection of subintervals, say j from 1 to n inside AB. Then this will sound very familiar because I've done this calculation in a slightly different context before, when showing why integrating L1 functions produces AC functions. So then u composed with gamma of tj plus 1 minus u composed with gamma of tj, right, is less than or equal, because it's an upper gradient, so integral over part of gamma restricted to tj and tj plus 1 of rho ds, which by definition is from t1 to t2 rho o gamma t, or maybe this is better writing this way, dt. This tj and tj plus 1. Okay, so for every j this is true. I also change my pen back to this. Notice that by definition, by assumption and definition, that rho gamma t dt from A to B is finite. So rho o gamma belongs to L1 of AB. It's an L1 function. Now let's do a summation in star. So doing sum in star yields that summation of u o gamma evaluated at tj plus 1 minus u o gamma evaluated at tj summing over j is less than or equal, because these intervals are disjoint, we get union over j of the subintervals tj plus 1 of rho o gamma t dt. But now rho o gamma is an L1 function, so for every epsilon positive there exists a delta positive, such that if L1 measure of a set E is less than delta, then integral of rho gamma t dt over E is less than epsilon if E is measurable, subset of AP. Measurable, then this is true. That's from absolute continuity property of integrals. Thus, for this epsilon, for this delta, if summation of tj plus 1 minus tj over j is less than delta, that means this union of intervals as our set E has measured less than delta, which means that this integral, let's call it this heart shape, is less than epsilon, which means that the other side, which was the summation of u o gamma oscillations over j is less than epsilon, and that's the end of proof that so u o gamma is absolutely continuous, because we've shown that for every epsilon that you fix here, you can find such a delta, and that is exactly definition of absolute continuity. So what did we prove? We proved that if you have an upper gradient along a curve, and the total integral of the upper gradient is finite, then you get an AC function on gamma. So this was just a situation with one curve. In my next video, which will be a bonus video, I will discuss this subtle issue of can you go backward? So if U is AC on gamma, does that imply that U has some integrable upper gradient along gamma? And after that, I will continue with discussion of upper gradients, not along one curve, but in general on the whole space. Until that, have a good one, and enjoy your holidays and subscribe to my channel.